So, for instance, you know, the whole speed, velocity, and acceleration, this is what I had to say about it. Let's see. Okay. So actually, this that you're seeing kind of quickly written up there, I have that. It's called review pages. So that's out there under Twitter too. And I think it's, bless you, it's out there under Twitter. It's also under doc sharing for the class. So this that you're going to see is already available to you.
Okay, so we can find like exactly what you write on there.
Exactly. Okay. Yep.
So better to just listen instead of trying to write it all.
Yep. Okay. Yep. I just have them handy just in case. But,
all right.
But yeah, exactly. You got it. It's like whew, because yeah, it goes up there fast. And but what I tell students at the review session is like your Unit 2 exam has the last section, which is short answer, right? And so what I did this time was to look at basically 2 questions for your homework, and they ended up being on your exam. So you know what I'm saying? So some of you are like, oh, we had a homework like that. Well, yeah, because that's going to be on your test too. Okay, so for instance, I think you had a homework like this. It's like, what's the difference between speed and velocity and acceleration? Okay, so basically speed is distance divided by time. Velocity is speed but also gives direction, and acceleration is change in velocity. Okay, the units for acceleration, that was also a homework question, is meters per second squared. Or distance per time squared, but meters per second squared is a good one. Newton's 3 laws, and I didn't put them here, but just be able to state them and give an example. That's not working. Come on. Okay, so Newton's 3 laws, be able to state them and give an example. Laws of motion. Mass versus weight. Mass is the amount of matter in an object, and then weight, though, is, and I put it here in red. Weight actually then is force created as gravity acts on mass. Okay, so that's kind of the difference between them. So if you visit the moon, okay, the thing about that is since the moon is less massive than the Earth, then the force of gravity is less. So actually your weight on the moon is 1/6 of that on the Earth. So you weigh 1/6 of what you weigh on Earth. But your mass is the same because the amount of matter you have is the same when you go visit the moon. Okay, kinetic versus potential energy. Kinetic energy is energy associated with motion. And potential energy is the energy stored energy, the energy associated with position. The E is equal to mc squared, Einstein's equation. Basically, m is a small amount of mass will be converted into a large amount of energy. Okay. Because the reason for that in this equation anyway is because c, the speed of light, is very big. So a small amount of mass makes a large amount of energy. Okay, Newton's law of gravitation looks like this, where force of gravity is equal to the big G, m1, m2 divided by, that's an r down there, not a v, r squared. So you guys know that the m's are masses and the r is the distance between the objects. And angular momentum. That's we left on that today. Talked about the solar nebula getting smaller. Basically, it had the same mass, but its radius was smaller, so its velocity went up. Tides are created due to the moon's gravity, gravitational influence of the moon. We talked about 2 types of tides. There are the neap tides, which are the diminished tides. They're at the quarter moons, and the spring tide are especially high tides. And they occur at full new moon when the sun is in line with the earth and moon. And then on to chapter 5. So here are the cousins listed at the top there. Different forms of electromagnetic radiation. Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. And they're written actually from short wavelength to long wavelength. But the short wavelengths have high frequency and the long wavelengths have low frequencies. With regard to wavelength and frequencies, for electromagnetic radiation, if you take any energy, actually its wavelength times its frequency is equal to c, the speed of light. Then the next kind of several go together, atoms, ions, and isotopes. So here's a picture of an atom. So that's the nucleus, and in the nucleus we have protons and neutrons. And then we have electrons outside the nucleus. Okay. An ion is an atom that has lost electron or gained electron, either way, lost or gained electrons. So a neutral atom, this is to say, will have the same number of protons as it does electrons. Isotopes are atoms of the same element, but they have a different number of neutrons in their centers. Atomic number is the number of protons, and atomic mass number is the number of protons plus neutrons. There's a delay. This isn't. Come on. Electrons can actually jump between energy levels, and I have a couple of figures over here to kind of look at that. We said that they can go from a low level to a high level, and then energy has to be put in to do that. And it will create these absorption lines, these dark lines, okay? The other scenario is that you have an excited electron that will go down to a lower energy, and it will emit energy, and it will create these emission lines, spectra, or bright lines. Ways in which light interact with matter. Matter can actually emit light, or matter can transmit light. Matter can absorb light, and matter can scatter or reflect light. So now when we say light, we mean all forms of electromagnetic radiation, not just visible light, but all of that stuff up there. So up there under visible, that cousin, I put the Roy G. Biv, like the colors of the rainbow, how are they with regard to wavelength? Well, red is the longest wavelength, and violet is the shortest wavelength. The stars, actually that was a homework question. We had two colors of stars. The blue star is hot and the red star is cool. Not only will the hotter star be blue, but it will also be brighter, and the cooler star will be dimmer. And the Doppler effect, we said basically there is motion between an object emitting either light or sound and the observer. Okay, that's how it works. And then we have these two scenarios. We can have a blue shift or a red shift. The blue shift is when their distance is getting shorter between them, so they are moving together. Okay. The red shift is when the thing is moving away. The next one, the two types of telescopes. We have a reflecting telescope, uses mirrors, and a refracting telescope uses lenses. And then in radio astronomy, we said that those wavelengths are so long that you have to have a humongous telescope, and or telescope area must be large, and or you need to use more than one dish. That's called interferometry. And then on to chapter 6, which we just did, with the whole solar nebular theory. So Earth got its water from comets, crossing the frost line and depositing the water. Over here in this table, the check marks are next to the 4 components that were in the solar nebula. And the most abundant is the hydrogen and helium, and the least abundant was the metals. Actually, I'm telling students who come in for a review session that if you want to add one more bullet, and again, this will be available to you as a review page, not the video, but that'll be available too. But you want to add frost line to your list of terms there. So the frost line we said today was the thing between Jupiter and, I wonder if I'm getting too far away. The frost line was the thing between Mars and Jupiter. So actually, if I were to kind of superimpose the frost line on our composition over here, I would put it between the rock and the hydrogen compounds. And here at the bottom is a figure we looked at today, okay, that actually kind of shows you the solar nebula was large and had lots of potential energy, and it got smaller, noticeably smaller, less gravitational potential energy, and more lots of thermal kinetic energy, which is important for our sun to turn on. General characteristics of the two types of planets, a table from your textbook. They differ by size and mass, and of course the density. The terrestrial planets are more dense. The terrestrial planets are made up of rock versus gas. The terrestrial planets have a solid surface. The terrestrial planets don't really have moons per se, even though we've got a great one, and they're warmer surfaces, and that's compared to the Jovian planets. The formation of the moons around the Jovian planets. So this is actually something we just looked at too, where the center thing in there is the sun, okay, and this kind of inset is Jupiter. So Jupiter actually kind of has a little swirling cloud around it for the moons to form. The term planetesimal is just kind of a precursor to a full-fledged planet. Okay, it's like a pre-planet. The next two kind of go together. Stuff that didn't make it into a planet were asteroids and comets, and they differ by what they're made of and generally where they are. So with regard to location, you figure the asteroids are on this side of the frost line and the comets are on the outside of the frost line. Okay. With regard to composition, the asteroids are rocky and the comets are rocky and icy. Dwarf planets, of course, Pluto is a famous dwarf planet. And so here I kind of said a dwarf planet will orbit the sun. It will be spherical because it's kind of big, dwarf planet, but it has not cleared its orbit. That's why Pluto failed. Asteroid belt located between Mars and Jupiter. And exceptions in our solar system, I put the Earth's large moon and then the backward rotating planets of Venus and Uranus. Those can both be explained if you had basically it got hit. We had extra stuff running around the solar system, and those are from bombardments, impacts. And that's it. So, yeah.